Hello and welcome back. In this video we will look at examples of how to add and subtract vectors, and in particular here we're asked to find the magnitude of the resultant force. And this is a good place to mention that quite often things like force and speed or velocity are often given in terms of vectors. And why is this? Well, a force is when you force something, you're essentially pushing on something or pulling on something. But when you push something, not only are you pushing it with some amount of strength, so there's a size to that force that you're using, you're also pushing it in a direction. So force, to describe a force completely, you need to describe what direction the force is going in, which makes it a vector. So here, maybe we have some object O, or some object, and it's being pushed with 2 pounds of force in one direction and 5 pounds of force in another direction. And those forces are acting with a 30-degree angle between them. But we want to know what's the resultant force. Because of this being pushed 2 pounds a little bit to the left and 5 pounds a little bit to the right, well, which direction is it actually going to be moving in? What the overall force? What direction is that going to be in? And how big is that? So here we're just asked to find the magnitude of this force. So again, a resultant is going to be the sum of two vectors. So I'm going to take this and I'm going to draw a nice just a copy of this over here. So we've got our vector OP. And then we have our vector OQ, which is pointing more or less over here. And then if I draw my parallelogram, which is how I add vectors together, this is my OQ. The resultant force is going to be the vector that starts at the beginning and ends way over here at the end. So this is going to be the resultant force, and this is what I want to find the length of. So I want to find the length from here to here. I know that the length of OP is going to be 2. The units are pounds. The length of OQ is going to be 5. 2 and 5. And this right here is a 30-degree angle. So that's the entire angle from there to there. So I don't really know what the individual angles are. I don't know what this little angle up here is, and I don't know what this little angle down here is. It's not, in general, going to be exactly half. It's not going to be 15 and 15. It could be split up, maybe 10 and 20 or 5 and 25. So we'll have to use a little bit more. But there's a lot going on here that we can fill in a lot of information. This is a 30-degree angle. And I have a line across the bottom. I have a line across the top, and these are the same vectors, so they are pointing in the same direction. So those are parallel lines. And for instance, I have this line coming up here. This vector, this angle up here, is also going to be 30 degrees. Again, this is simply because this is like opposite interior angles. These are going to be 30-degree angles. But then the vector over here, the angle over here, when I compare this angle up here and this angle, these are going to be complementary angles. They should add up to 180. You can see that if I put this angle up here, it's going to be pointing in a straight line, which is 180 degrees. So this guy is going to be 150 degrees. And why? Because that's 180 minus 30. These guys are complementary angles. Not complementary, supplementary angles. I used the wrong word. And again here, this guy is also 150 degrees. Again, for the same reason that these angles are the same, these angles are going to be the same, sort of opposite interior angles. So I have my triangle up here, and maybe I'll just use this triangle out on top. So I've got my OP and my OQ, and then the sum of those two vectors. I know that this length is 2, this length is 5. I have a 150-degree angle in here. And I want to know the length of this side. This is time to break out the law of cosines, because I have 2 side lengths and 1 angle. So if I call this side, let's just call this C for the moment. I know that C squared is going to be that length squared plus this length squared minus 2 times the first length times the second length times the cosine of the angle between them. I'm running out of room here, so let me just plug in a bunch of numbers in here. So this is going to be C squared is going to be equal to 2 squared plus 5 squared minus 2 times 2 times 5 times the cosine of 150 degrees. And that's going to be C squared. So let's jump over to our calculator, and we'll take 2 squared plus 5 squared minus 2 times 5 times the cosine of 150, and I'm in degrees, so that's all good. So this is going to be 46 point, and I'll just round it to 32. And that's C squared. So C itself is going to be the square root of that guy. So I just want the square root of my previous answer. And if I round it to 1 decimal place, it's going to be 6.8. And that's going to be in pounds. So let's take stock of what we've done. We've said that we have 2 forces that are acting on some object, and we want to find what's the overall force acting on the object. How much force is being applied. We've got 2 pounds pointing in one direction, 5 pounds pointing in another direction. They're both almost in the same direction, but not quite. And we were able to sort of draw our parallelogram and fill in a lot of details. If this is a 30-degree angle here, that means opposite it's also going to be 30 degrees. But we have a supplementary angle going on the opposite side. So this is going to be 150 degrees. And then again, the opposite interior angle, we can say that that's also going to be 150 degrees. So we know all of the angles in the parallelogram. And just by taking this triangle up here, I know one side length is 2, one side length is 5. The angle between them is 150. The law of cosines will give us the length of that last side, which is going to be the resultant force. So overall, there's going to be 6.8 pounds of force. Not quite 7. If they were pointing in the same direction, it'd just be 2 pounds of force and another 5 pounds of force. They're not quite pointing in the same direction, though, so they're going to cancel each other out a little bit, but not a whole lot. It'll still be 6.8 pounds of force. This method of drawing the parallelogram and drawing all these angles is going to be very, very helpful. So let's look at this guy. A plane is going to have an airspeed of 100 miles an hour with a bearing of 0 degrees. And here I want to be very explicit. So we're talking about speed or velocity. So again, we can talk about how fast we're going, but not only how fast are we going, what direction are we going in? And we're given airspeed, and I'll come back to that in a second. But there's a wind, and the wind is blowing 20 miles an hour at a bearing of 150 degrees. Maybe I'll change that to 170, since our last question already had 150 degrees in it. And then we want to find the ground speed and bearing of the plane. We're given airspeed and we want to find ground speed. What's the difference between these? airspeed is essentially what the plane feels like it's going. So the plane will either have propellers or jets, and it's going to be pushing itself forward at 100 miles an hour, going straight. So maybe we can draw a picture. So 0 degrees is 0 degrees from due north. So our plane feels like it's flying due north at 100 miles an hour. But then there's a wind blowing 20 miles an hour at a bearing of 170 degrees. So 170 degrees, 180 degrees would be pointing in the exact opposite direction. That would be due south. 170 degrees is pointing nearly due south. So that's going to be blowing 20 miles an hour. Almost south. So the plane, even though it's pushing itself forward, trying to go 100 miles an hour, the wind is blowing 20 miles an hour nearly backward. So the plane is actually going to be pushed a little bit slower than actually 100 miles an hour. So if we were standing on the ground and we looked up at this plane, we wouldn't see it go 100 miles an hour. We'd probably see it go a little bit less because it's being pushed back a little bit. So the question is, what is its ground speed? If we looked up at the plane, how fast would it be going to us? And what direction is it going? It's pushing itself forward at 100 miles an hour, straight north, but the wind is going to be pushing it a little bit back and a little bit to the right, a little bit to the east. So the actual direction of the plane is going to be a little bit different. So we just need to find the actual ground speed and bearing of the plane, which we can draw a picture. So again, our plane is trying to travel due north. And let me scale this up a little bit, just so it'll be a bit easier. So we've got 20 miles an hour nearly due south, but a little bit to the right. And our angle in here is going to be 170 degrees. Well, the plane, if we want to find the resultant here, the result of combining our airspeed and our wind speed, we are going to be adding these vectors together. So the plane itself, the resultant vector is going to be right here. So you can see that it's going to be traveling a little bit slower because it's being pushed back by the wind, but also it's going to be pushed a little bit to the right since the wind is blowing roughly to the south east. So the question is, what is the length and bearing of that of this new vector? Well, just like before with the parallelogram, parallelograms are very nice. If we know that this angle is 170, we know that this angle up here is also going to be 170 because they're going to be opposite interior angles. But the angle up here is going to be a supplementary angle. I've got a straight line and two parallel lines crossing that. Those angles are going to have to add up to 180. So what would add up to 180 with 170 degrees? That's a 10 degree angle, a pretty small angle, and essentially that's going to be 180 minus 170, and that gives us our 10 degree angle up there, but also 10 degrees down here because of the opposite interior angles. So now what I can do is I can draw this, draw the triangle up here, and we'll go to town using all of our information. So we've got our 10 degree angle. We know that the plane is going 100 miles an hour, and the wind is trying to push it back, and that's going 20 miles an hour. So we can find the actual speed of the plane by using our law of cosines again, and we'll use the law of sines to find the angle at which it's flying. And I'll do this in the next video.